All right, good morning, everybody. So in the last lecture, we were talking about implementing a linear data structure using a linked sequence of nodes. And so we're going to implement a stack in today's lecture. So just to quickly remind you how this thing's going to work. So a stack, in a stack, it's a linear sequence of nodes. It's a linear sequence of elements. You can only do something with the top element of the stack. In our stack, we're going to use a linked sequence of nodes. So we're going to keep track of the node that represents the top of the stack. So this thing top is a pointer to the top node of the stack. In an empty stack, there is no top node, so top is just null. If you have one element on the stack, top points to that one node containing the element. Inside the node, we have our value here. We're implementing a stack of int. So we have the 1 stored in the node. The end of the sequence is indicated by having a link in the node that is null. So the next link of that node points to nothing because there are no more elements in the stack. As you add elements onto the stack, the sequence becomes longer and longer and longer. Of course, as you pop elements off the stack, it becomes shorter and shorter and shorter. Everything happens at the top of the stack. In our implementation, we're going to keep track of the top of the stack and how many elements are in the stack. So here we would keep track of this pointer here, and we would say that there are 3 elements in this stack. All right, so we're also going to implement our type as an opaque type. So in our string type, people could see inside the structure that represented the string. Also, people knew that it was a structure that was representing the string. In an opaque type, you don't tell people how the thing that you're implementing is represented, which is why it's called opaque. And so most opaque types, you get a type name, and that type name is declared with something called a type def. So a type def statement lets the programmer create a new name for some other type. And you can use this anywhere. You don't have to use this with type defs. So for example, you could, if you don't like the name int, you could give it a different name. So you could type def it to a different name, and then you could use your other name if you wanted to. That would be unusual, but it's perfectly legal in the language. Right? So type def simply says your new name is simply a name for an existing type. So the way a type def works is it's the keyword type def. Then it's the name of the existing type, right? Followed by your alias, so the name that you would like to use instead of the name of the existing type. So for example, if you wanted to type def QString, our QString implementation, right? So you don't want to write struct QString everywhere. You can use a type def to write something shorter. So you write type def somewhere, right? The name of your existing type. So remember, for structures, the keyword struct is always part of the name. And then the name that you would like to use instead. So I'm going to use QString everywhere instead of struct QSTR. Right? And now, in the rest of your program, as soon as you've declared the type def, you can just use the name QString everywhere instead of struct QString. Right? So here we can write QString star course, so a pointer to a QString, right? Or a pointer to a struct QString, right? And then call one of your QString functions to create the QString. Right? So arguably, that's a little bit easier to read than this. Right? So right? You've got one word here or one name here instead of the struct followed by a name here. So this is arguably easier to read. Many C programmers will say you shouldn't use type def in this particular example. Right? So the reasoning why is because if you have a structure that you're using for some reason, it's useful to know that the thing actually is a structure. Right? You want to know that you can actually, so given that you know it's a structure, you probably know what's in the structure. So it'd be nice to know that you can access the members of the structure using either a dot or the arrow notation if you have a pointer. Right? So if you just use a plain old type def like QString, right? The casual reader now no longer knows that this thing actually is a structure of some kind. So several prominent programmers, in particular Linus Torvalds, so creator of the Linux kernel, says don't do this. But it's pretty common nonetheless. All right, so there is something funny about typedef. So here we've got a structure whose tag name is QString, right? But the tag name for structures, it lives in what's called a different namespace than other names. And so what that means is that you can use the tag name QString, but you can also use the alias QString. And this is perfectly legal. It's confusing, but it's legal. Right? So as soon as you write that typedef, you can now just write QString everywhere instead of writing struct QString. And so you are allowed to give, the alias name can match the tag name if you want to. Again, this is generally a bad idea. It becomes a little bit confusing to read your code. So instead, I'm going to use, for the tag name on a structure, I will write _tag after the tag name if I'm going to use a typedef somewhere. So for our stack, it's going to be represented as a structure. The structure tag name will be qlstack _tag. I'm going to use the typedef qlstack instead of writing struct qlstack _tag everywhere. Simply to illustrate the use of typedef. All right, so now we're going to go ahead and implement our stack. Remember, it's an opaque type, so when we declare the stack structure, we're not going to tell people what's in the structure. So there's our include guard. I'm going to include standard bool because I'm going to want to use true and false. And now here's the typedef. There's the forward declaration of our structure. Right, so typedef struct qlstack tag qlstack. What the heck does that say? It says two things actually. So number one, it says there exists a structure called qlstack _tag. Right. We don't know what's in it, so we haven't defined what's in it. We're simply saying this thing exists. Right? And furthermore, we're saying whenever we write just plain old qlstack, we actually mean struct qlstack _tag. So that thing actually does that typedef actually does two things here. Right? Somewhere else we'll actually define the structure, but not here. Okay, and now you just put in the functions that you want for your stack. Right? So you probably want something like make a new stack. You probably want get the size of a stack. Is the stack empty? Push something onto a stack, pop something off a stack, so on and so on and so forth. Right? So qlstack _init is our function that makes a new stack and returns a pointer to the stack. Right? So it's an empty stack. That would be like a no argument constructor in Java. Right? But remember again, C doesn't have constructors, right? It only has functions. Okay, qlstack is empty. So this one requires the caller pass in a stack. It's passed in as a const pointer, indicating that the function is not going to modify the state of the stack. That's good, right? If you're checking if the stack is empty, you don't want to push or pop elements off the stack. So that returns true or false. True if the stack is empty, false if the stack has some elements on it. Return the number of elements on the stack. So that's qlstack _size. Right? Again, takes in a pointer, const pointer. Right? So evaluating the size of a stack doesn't change the state of the stack. There's our push function. So push requires a pointer to a stack that we're going to push the element onto. This is not declared as a const pointer. We have to change the state of the stack that we're pushing the element onto. Right, so that can't be const. It's a stack of int, so there's the element that we're going to push onto the stack. And this function returns back a pointer to s in this case. If something goes wrong, we return null to indicate that an error has occurred. Pop is similar. So pop is similar in that it returns the pointer to the stack that was passed into it. Right, so this will normally return s. It'll return null if something went wrong. Now, if we're going to pop an element off the stack, the caller probably wants the element. So we need some way to return the element back to the caller. I've already used the return value to return the stack or null. And so I need some other mechanism to return the value back to the caller. Right? We know how to do this now. Right? You ask the caller to pass in a pointer to an int that we can write into. So this function writes into the int object given by the caller. right? And so the value that's popped off the stack gets written into the object pointed at by popped. Okay, we also have a print function that prints the elements of the stack, and I'll show you how that works shortly. And finally, just like with the string, because the stack is being dynamically allocated, also the nodes of the stack are being dynamically allocated. We need to provide a function that lets the caller deallocate all the memory used by a stack. Here we have to, right? So for the string, we didn't have to. The string, the caller can free the structure and the underlying array themselves. Here, the caller can't free the nodes of the stack because they don't know that this is a node-based stack. Right? They have no idea how this thing is implemented because all that they see is that it's a structure of some kind. Right? They don't know what the name of the members of the structure are, and they don't know how the structure is implemented. Right? So there's no way for them to actually free the elements, the nodes storing the elements of this particular stack. So we have to provide them with a function that can free the memory for them. All right, any questions so far? Okay, most of these functions are pretty easy to implement. There's a couple of things that you have to be aware of though. Okay, so where do we implement the stack? Well, you create a source code file, qlstack.c, and that's where your implementation goes. If you're in 124, you haven't seen a linked stack yet or a linked sequence of nodes, but in 124, you will shortly see one. So in Java, the way you implement this thing is you create your class called linked stack or just stack, whatever you want, right? And then internally, you create another class that represents the nodes of your stack. Right? So here we have a nested class. So C, you can't have, in C, oh, that's not true, you can't have a nested structure. So we're not going to do a nested structure in C. We're going to create two separate structures for our C implementation. One of our structures basically represents that class there. We're going to have a separate node structure that represents that class there. Inside your linked stack, you'll have a couple of fields, right? You'll have a reference to the top node of the stack, and then you'll keep track of the size of the stack. So this is all in Java, right? You're going to do the exact same thing in C, right? So one structure for linked stack, one structure for node. So there's our node structure, right? Every node holds one int, that is the element stored in the node, right? And then it has a pointer to the next node in the sequence, right? So here we have a pointer to the next node in the sequence, and that's it, right? I chose not to call this node underscore tag because this class, this structure is internal to QL stack itself, right? No one's going to see this structure outside this source code file. So I'm not going to try to hide the, I'm not going to try to do anything unusual with the name, right? I'm just going to use struct node everywhere. For our stack structure, it keeps track of the number of elements in the stack, right? And it keeps track of the top element of the stack, right? And so it's a pointer to the top node of the stack, right? And now, so that's it. So that defines the data that's used to represent a stack. Right, one node type, one stack type, right? Inside each type, you've got just a couple of members. Okay, so we're now ready to do init, right? So init makes a new stack, returns a pointer back to the new stack. Oh, I called this new here. I think it's init on the previously, isn't it? It's init, right? I wonder why it is. There's a typo here. One of these is, this is either new or init. I don't remember which way it actually works, but there's a typo here. I think, hang on, just let me quickly check. Yes, I think there's a typo somewhere. All right, so that's either init or the other one's new. I don't remember which. Regardless of which name it actually is, its job is to allocate a new structure for the stack, right? So you're going to call malloc, right? Or calloc if you want. Right? So we're going to allocate memory. We're going to ask for memory that can hold one stack structure, right? And we're going to return a pointer. We're going to return s back to the caller in this case. Right? Do a little bit of error checking here, right? So if malloc fails, return null, right? And then now don't forget to set the members of the structure because when you malloc something, the memory is completely uninitialized. right? So we have to go in and set top explicitly ourselves, right? In an empty stack, there are no nodes, so top is null, right? There are no nodes, so the size is 0, right? And then return s. So compared to a Java constructor, the only thing that's new here is, the only thing that's really different here is the explicit call to malloc, right? In Java, the malloc gets hidden behind new, right? So new stack, right? The new part is actually doing the malloc in Java. Okay, so there's our initialization function. Not terribly complicated. Size and isEmpty are even easier. Right? If you want to know the size of a stack, well, you just return size. Right? If you want to know, is the stack empty? Well, you just ask it, well, is size 0? Right? And away you go. So those functions are pretty straightforward. Push is the function that takes an element given by the caller and pushes that element on top of the stack. Now remember how this is going to work for us. We're going to make a new node, we're going to store the element in the node, and then we're going to hook that node up to the current top element of the stack. The making the new node part is the part you have to be a little bit careful about. Okay, so here's what it looks like. So we're going to push onto the stack s the value given by elem. Right? So if someone gives us an empty null stack, right? So if someone passes in a null pointer, obviously you can't push onto that stack. So if someone passes in a null pointer s, we're going to return back null. Right? So instead of trying to dereference s or trying to use s to do something with a non-existent stack, probably causing an error, right? We're going to return back an error value here. Okay, so when you push something onto the stack, you have to make a new node, right? So there's going to be a call to malloc. And so there's your call to malloc. Now remember what happens whenever you call malloc or calloc or realloc, right? At some point you have to free the memory that you just allocated, right? You're not going to free it here, right? You're going to, because you want to keep, you want that node to be on top of the stack. So you don't want to free it in here, but somewhere we're going to have to free that node. So you have to keep, you have to remember in the back of your mind, okay, there has to be a call to free for every node that we create. Right? And you'll see shortly where we're going to put that call to free. Again, do a little bit of error checking here. If malloc fails for some reason, return null. So ran out of memory, can't push an element onto the stack. Right? Once you've got your node, just go ahead and fill in the node. Right? So we want to put the element into the node. So n-elem is just equal to elem. Right? We now want to make the next pointer of our node point at the current top element of the stack, right? So we know what a pointer to the top element of the stack is. It's just s-top. So we want n-next to be assigned the value s-top, right? So we just hooked our new node up to the current top node of the stack, and now we have to adjust the members of the stack, right? We've got a new top node, so we need to write s-top equals n. Right, and we've just increased the size of the stack by 1, so we need to add 1 to the size of the stack. Right, and that pushes an element onto our stack. We can now return the stack back to the caller. Okay, so that's the line we have to remember. This forces us to remember that we have to free the node somewhere. Right? And so where does it make sense to free the node? Well, it makes sense to free the node when you're done with the node. When are you done with the node? When you pop the element off the stack, you're done with the node. So in pop, there's going to be a call to free. Right? So popping an element off the stack returns the top element back to the caller, removes the node from the stack, releases the memory that was allocated to the node, and then adjusts the stack so that the top pointer now points at the next node in the sequence. So again, if someone passes us a null stack or a pointer to nothing, we return null. Right? We want to return the element that's stored in the current top node. Right? So we also want to free that node. So I'm going to make a temporary variable called old top. and I'm going to make that equal to the current top node. I want to rewrite the element that's stored in old top into popped. So I'm going to get the element out of the current top node. Right? Okay, so now remember what I have to do. I have to adjust the top pointer of our stack to point at the next element in the stack. Right? And so the only way I can get to the next element in the stack is if I look at the current top node, and follow its next pointer. Right? So old top next is the next node in the stack. Right? If there's only one node in the stack, old top next is null, which is fine. Right? So now S top is null. Right? If there is another node in the stack, old top next points at that next node. So we want to set S top to be equal to that next node. Right? And then we want to decrease the size of the stack by 1. Right? I've got the old element, right? So I can return that back to the caller. I can write that value into the caller here, right there, right? And I can free the old top node, right? I no longer need the old top node. I've remembered what the element was in the old top node, right? So I don't need it anymore. I can free the old node, right? So that free is the matching free to that malloc, right? So that's good, right? We've deallocated the memory that we've used. All right, so our function here is a little bit more sophisticated than it first appears. Right? If someone passes in null for popped, we're going to interpret that as meaning the caller doesn't care about the value of the popped element. Right? So if they pass in a non-null pointer for popped, we're going to interpret that as meaning please write the value into whatever is pointed at by popped. So we check if popped is not null, right? Go ahead and write the element into popped. So dereference popped, right? Store the value elem into the object pointed at by popped. Right? Now we're done everything, right? We've removed the element, written the element into the caller's value, or the caller's variable pointed at by popped, right? We've deallocated the memory needed by the old node, and we've adjusted the stack size and top pointer so that they now point at the correct element. So we're finally done. We can now return a pointer back to S. Right. Okay, any questions so far? Great. There is one other situation where you might want to free the memory allocated to a node, right? And so that is if someone calls stack free on a stack that has a bunch of nodes in it, right? So if someone frees a stack and the stack is not empty, right? It's now our job to have to free every node that's in that stack, right? And so that's what stack free does. So again, if you're in 124, this is the first time you're going to see iterating over a sequence of nodes, right? And so this is what we have to do, right? So in a stack, we've got a linked sequence of nodes. We're going to start at the top, and we're going to free the top node, right? We want to go to the next element, free the next node. We want to go to the next element, free the next node, and so on and so on and so forth. So we have to follow this sequence of linked nodes. So to free a stack pointed at by S, right? If S is already null, there's nothing to do. Right, so we return. Now we want to free every node in the stack. So starting at the top node. So N is going to be a pointer to the current node in the sequence. Right, so starting at the top node, right? While N means while N actually points at a node, right? Eventually N is going to hit null, right? And then so we know there's no more nodes in the sequence. So while there's still a node in the sequence, right? I want to free the node N, but before I do that, right, I have to remember what is the next node in the sequence. If I free the node, I can't get to the next node in the sequence, right? So before I free the node, I remember what is the next node after N, right? Store that value in next, or some other variable, it doesn't matter, right? Now that I've remembered what's there, I can go ahead and free N, right? So there goes the node, right? The memory allocated to the node now disappears, right? And we now want N to point at the next node in the sequence so that we can free the next node, right? So N now gets the value next, right? So that starts at the top of the node. It remembers what's the second element or the second node in the sequence, right? It frees the top node, and then it goes to the next node in the sequence, right? Eventually, right, because you're following the next link every time, eventually you hit the bottom node, right? And n next is null, right? And so the next time through the loop, n becomes null and the loop doesn't run. Right? All right, so once you've freed all of the elements of the stack, you now have to free the stack itself. And so there's your call to free, that frees the structure that represents the stack. Right? And so we've taken care of cleaning up after ourselves, right? So for every call to malloc, there is a corresponding call to free, right? Every time we pushed an element onto the stack, we called malloc, right? We're now going to go through all the elements and free each one, right? When we created the stack, there was a call to malloc to allocate the structure, right? There's the call that frees the memory allocated to the structure. Right. Okay, what about printing a stack? So printing a stack is pretty straightforward, right? So to print the elements of a stack, you probably want to print the individual ints in the stack, right? You want to arrange them somehow. So you can arrange them from top to bottom in a line, on multiple lines, right? I'm going to print them out from left to right, separated by commas and spaces. If the user wants to, they can put a string before the stack and a string after the stack. So pre is the string that shows up in front of the elements of the stack, right? And post is a string that shows up after all the elements of the stack have been printed. Right? Okay, so we're going to print these to standard output, so we're just going to use printf to print everything. Right? So if someone gives us a string pre, so if pre, right? If they don't want a prefix, then we just they just pass in null. Right? If they give us a prefix, print the prefix. Right? The prefix is just a string, so we just use %s to print the string. Right. Oh, that print top. Sure, I guess we can do top and bottom here. Right. I guess now we're going to print out top to indicate this is the top element of the stack. Right? And now we want to iterate over the sequence of nodes. Right? So if the stack is not empty, visit every node. Every time we visit a node, I'm going to print out the value in the node. Right? If there's more nodes left in the sequence, I'm going to print out a comma and a space. Right? So I'm actually going to do this slightly differently. So the first thing I'm going to do is I'm going to print out the top element. Right? So starting at the top, right, I'm going to print the element at the top. Right? I now want to advance n to the next element in the sequence. Right, so that n now points at the second node in the stack if it exists. Right, now as long as there's elements left to print, right, so while n is not null, right, I'm going to print out a comma and a space, and then the next element in the sequence, and then the element pointed at by n. Right, so print out the first element, right, and then every element you print thereafter has a comma and space in front of it. Right. And so you print out the next element, advance n to point at the next element in the sequence. Right. So right there is so you set n to top, right? And then you write a little loop that looks like while n. Right? At the end of the loop, n equals n dot next, and that's the general pattern for iterating over a sequence of nodes. Right? Start at the top node. Right? While the top node, while n actually points at a node, do something with n, or do something with the element in n, right? Advance n to the next node in the sequence. We then print out bottom to indicate that that's the bottom element of the stack, and then we print out the postscript if the caller passed in a postscript string, right? And that's printing out a string, right? So the print and free both functions show you how to iterate over all the nodes in a sequence. Right? It doesn't matter if you're implementing a stack or a queue or a list, right? The pattern's always the same. Okay, so does this thing actually work? So there is a little program called demo.c You pass it in a bunch of integer values on the command line, and it makes a stack using those integer values. And then it does some stuff with the elements. Right? The program is not actually important. I'll run it so that you can see what it looks like. Right? Oh, sorry. So that makes an empty stack. So let's make the stack 1, 2, 3. Right? So 1 gets pushed onto the stack, then 2, then 3. Right? There's our stack with 1 in it. Then I think I negate the elements in the stack. So we push the elements onto the stack. Yeah, push the elements onto the stack. Oh, we make 2 stacks, I see. So we make the first stack, we're going to push the element onto the stack. On the second stack, we push the negative of that value onto the stack. And then we print out both stacks. And then there's another loop that pops the elements off the stack, off one stack, off the first stack, and then pops the elements off the second stack. And then we free both stacks. Okay, so we push a 1 onto the first stack, we push -1 onto the second stack, right? Push 2 onto the first stack, push -2 onto the second stack, so on and so on and so forth, right? Then we start popping elements off the stack. So when we pop the first stack, we should get a 3, and we do. So there's the popped element there. The rest of the stack looks like 2, 1, right? And so on and so on and so forth. So it looks like this little test program seems to work. And our stack seems to support pushing and popping correctly. All right, so there's implementing a linked node-based stack where you know the element type of the stack. Anybody have any questions about what we've talked about so far? Okay, it now gets slightly more complicated. So in this particular stack, the elements are all ints. So if you wanted a stack of double, your only choice at this point is to reproduce all this code. Change your node so that it's a double instead of int. Change all of your functions so that they now either take in doubles or write double values when you pop them, right? And you have to give your new type a new name. Right, so now instead of QL stack, it's now called something else, right? QL stack D or something like that for double, right? As soon as you want a stack of string, you now have to do the same thing, right? I have to come in, I have to change the node so that it's now a pointer to a character, right? Representing a C-style string, right? Change all of my functions, give my type a new name, so on and so on and so forth, right? So for those of you who have taken 124, you know that Java has generics. Right, so you can make a generic stack. You simply tell the stack what type of element you want. You don't write any new code, right? And so the question is can you do the same thing in C? And so the answer is yes, but we're not going to quite do it the same way that Java does it, right? So now we want to make a stack that can hold any element type. And that complicates several of the things in our implementation. All right. So this is a linked stack of any element type, or generic linked stack, I think is the title of the notebook. Okay, so we kind of want to avoid having to create a new type every time by copying and editing the code, right? The edits that you have to make to the previous stack implementation, it turns out they're very small. It would be nice if the compiler could do the edits for us, but it can't. In C++ you can. So in C++ has these things called templates, and what I just described to you is almost exactly what the compiler does, right? So if you wanted, you make a templated type, so you make a templated stack type, and then you pass in just like Java, you pass in or you tell the type what element, a type do you want to use, right? So make a stack of int. The C compiler actually generates a new class for every type of stack that you create, right? So if you make a stack of int and you make a stack of double, you end up with two separate pieces of code that represent those 2 different stacks. It works in a completely different way in Java. Okay, so here in Java, just to quickly remind you, if you have a generic stack, you can make a stack of integer, you can make a stack of double, you can make a stack of any type that you want, right? And away you go, right? in languages that support generic types, the programmer defines the type once, right? And that's it. So you don't have any code duplication. Java's generic type mechanism is called type safe, right? So if I make a stack of integer, I can only push integers onto the stack. Right? If I try to push anything else onto the stack, the virtual machine complains, right? And so that's nice, right? From 121, you know that if you make a list in 121, you can put whatever you want into the list, right? You can put it in an int, then a double, then a float, and then a string, and then another list, and so on and so on and so forth, right? That becomes really problematic when you start taking stuff out of the list, right? I take something out of the list, what the heck is it, right? You have to remember what order did you put things into the list, right? So Python uses dynamic typing. So it provides collections that holds instances of any type, right? And so that's the sort of thing we're going to implement in C, right? We're not going to do the type safe implementation that Java has. We're going to create a stack in C that can hold elements of any type. It's up to the user of the stack to remember what elements are they pushing onto this stack. Right. Now, the question is how the heck do you store something of any type? Right? So remember, in our node, right, we know in our previous implementation, we knew this was a stack of int. So it's easy to give a type to elem, right? It's just int. So C has there's no generic type mechanism in C, right? So there's no way, in Java you just write T or something, right? C doesn't have that. The only thing that C has that can help us solve this problem though, is this pointer to void. Right? So remember what a pointer to void can store. It can store a pointer to anything, right? So it holds any pointer value, right? Also remember what it means, right? The thing that it points at is unknown to the compiler, right? And so you have to be careful when you use these things, right? You have to remember what it is exactly that you're pointing at, right? So void star means make me a pointer, right? It points at something, we don't know what, right? More precisely, the compiler doesn't know what, right? So a void pointer is a variable that can store a value of any pointer, right? You don't need a cast to store the value. If you want to get the value out, you probably want a cast. Okay, so to create a stack that can hold any element type, right, we can use a void pointer to store a pointer to the element, right? Now, if we do this, this requires the user of the stack to pass in pointers to elements instead of the elements themselves, right? So for the end user, this is slightly inconvenient, right? No longer are they working with elements, they have to work with pointers to elements, right? But the change to our node is very straightforward. Right? Instead of int, it's now void star. Right? Okay, so now remember what the consequences of working with a pointer is, right? So this pointer is going to point at something, right? So we're going to make this stack, we're going to keep track of a bunch of nodes, right? Inside each node, there's a pointer to some element, right? Those pointers have to remain valid for the lifetime of the stack. Right? So in other words, those pointers have to point at stuff that still exists as long as the stack exists, right? And so what that means is that the caller has to remember they're going to push something onto this stack, right? Either the stack lives as long as the elements do, right? Or the elements have to be dynamically allocated as well, right? So that imposes another constraint on the user of this type. So remember that line there, right? And also remember the consequence, right? So what does this mean? It means that memory for each element has to be probably has to be dynamically allocated. It's the caller that's probably going to want to dynamically allocate the elements, right? It's not the stack that's going to want it's not the stack that wants to dynamically allocate memory for storage. And in fact, the stack can't actually do it, which we'll see shortly. All right, so what does this thing look like? So it turns out this our new stack is going to look a lot like the existing stack. There are some important changes in the functions because we're storing pointers to elements instead of the elements themselves. Right? So instead of QL stack, it's QLG stack, G for generic. Right? So there's our type def. All of our functions, I think, do I have the header file? Yes, I have the header. Okay, the functions are all going to be similar, but because of the way we're storing elements, we're going to have to change some of the functions. In the source code, we declare the node. No, we don't declare it like that. That's for sure. Sorry, that's a mistake. Oh yeah, that's an error. I have to fix that on the on GitHub. Okay, so in the source code for our generic stack, again our structure for the node appears. Right? Instead of an int, we have a pointer to void, or a void pointer, sorry, here. Right? Otherwise, everything's the same. The stack itself, nothing changes. Right? We're still keeping track of the top node. Right? We're still keeping track of the size of the stack. Okay, so init or new, whatever it's actually called, works the exact same way, right? Allocate a new stack, right? Set the top pointer to null, right? Set the size to 0. So the new or initialization function works exactly the same way as before. Push has to change, obviously, right? So push before took in an int as the element. Now we're asking the caller to pass in a pointer to their element, and we don't care what element type the caller is using. So instead of taking in an int, we now take in a pointer to void. Right? Everything else, though the signature, otherwise there's no changes to the declaration of the function. Popping now gets a little bit more complicated. Right? So remember when we popped with an int stack, we wrote the popped value into a variable owned by the caller. Right? We know that it's an int. The variable that's owned by the caller has to be an int, so we require the caller to pass in a pointer to int. Now we're going to write the pointer that points at the popped element into a variable owned by the caller. Right? So now we want to write a pointer value into a variable owned by the caller. So what does that mean? The caller needs to pass in the address of a pointer variable, right? What does that mean? They need to pass in a pointer to a pointer, right? So popped is a pointer to some pointer variable, right? We can now write the value of elem into the pointer pointed at by popped, right? So now we have the double star here, right, to indicate pointer to a pointer. Now, fortunately, the implementations are almost exactly the same, right? So here's push, right? That's the same, right? That's the same. That's the same, right? That's the same. That's the same, and that's the same, right? So there's actually no changes to push, right? The actual implementation doesn't change, right? The fact that we switched this to pointer to void instead of int doesn't matter as far as the implementation is concerned. Pop also doesn't really change, right? We're still going to remember what the old top node of the stack is, or the current top node, right? We're still going to get the element out of the top node. Instead of getting an int, now it's a pointer to void, right? We're still going to adjust the top pointer so that it points at the next node in the sequence, right? We're still going to adjust the size down by 1. We're still going to free the old node, right? And we're still going to write the popped value, elem, into the variable popped, right? You don't need a double star here, right? It's still star popped equals elem, right? So we dereference that variable there, right? When you dereference it, you get a pointer to something, right? You get a void pointer, right? So you dereference it once, you get a void pointer, right? I can write elem, because elem is also a void pointer, right, into the value pointed at by popped. So there's one dereference, right? Store the value elem in the dereferenced variable. Right? So nothing changes there either. And so it looks like we're home free. Unfortunately, we're not. Right? So now you run into some problems. Right? And so when you look at the functions that print a stack, and you look at the function that frees a stack, right? Immediately you realize something funny is going on. Right? So when you print a stack, right? Previously when we printed a stack of int, we know how to print the int. Right? I know I can just use the conversion %d to print the element, and away you go. Right? So what's the problem in a generic stack? The problem is that the stack doesn't actually know what the elements are pointing, what the pointers to the elements are actually pointing at. So it doesn't know if it's a stack of int, or of a stack of double, or a stack of some mixed types. Right? It has no idea. So there's no way you can call printf here, which means there's no way that the function, as it's written now, can actually print the elements of the stack. And so that's a problem. Right? Now what about the function that frees the elements of the stack? Right? Okay, so when we freed the nodes, we just freed the node, right? So you just freed the pointers that the stack is keeping track of. But now, if you've got a stack of stuff, right? And the elements that you are storing in the nodes are pointers to other elements, right? The question is does the caller want to simply get rid of the stack and keep the elements, right? Or do they want to get rid of the stack and get rid of the elements as well, right? So they might want, when you free the stack, that you actually remove the elements from memory as well. The problem here is that the stack you can't free those elements because you don't know what it's pointing at, right? All you have is this pointer. You don't know if it's pointing at some other compound type, right? So it might be pointing, you might have a stack of structures where inside each structure there are there's an array that you need to deallocate. There's no way for the stack to know this, right? So there's no way that we can write a function that will correctly deallocate the elements that are being pointed at. Right? Okay, so who does know how to do all of this though? Right? So who knows how to print the elements? Well, whoever's using the stack, presumably they know what elements they pushed onto the stack. So the only one who might know how to print the elements is whoever made the stack. Who knows how to free the elements that are being stored on the stack? Well, again, presumably the user of the stack knows how they created the elements. So hopefully they know how to free the elements as well. Right? So the user of the stack is the one that knows how to print and free stuff. Right? And so in C, is there a way that we can ask the user to provide us with a mechanism that they define to print something or free something? Right? And so the answer is yes. Right? So in C, we can ask the user for a function that prints their element type, and we can ask the user for a function that frees their element type. Right? So for example, if the caller or the user of the stack, right, provides some function, not necessarily called this, right? So print my user-defined type, right? They provide a function that can print something to standard output, right? And it prints one of these, right? So it prints something that's pointed at by a void pointer, right? So if they can provide that function for us, right, we can ask them to, we can ask the caller to provide one of these functions, and then our stack can use that function to print each individual element. Right? So internally, this function needs to do something with that pointer. Oh, sorry, that's not true. Right? So the caller knows what their elements are what their pointers are pointing at, so they can tell us how to print. They can define how that print function works. Right? Similarly, if the caller can provide a function that frees one of their elements that is being pointed at by a pointer, right? Our stack can now use that function to free the elements inside of pop and inside of the inside of the stack free function. Okay, here we can use a const pointer, right? Because printing something shouldn't change the thing being printed, right? Here we cannot use a const pointer, because freeing something is going to change the thing being freed, right? So that can't be const. This one can and should be const, right? And so there's that's what this paragraph is talking about here. All right, so that's great. So we're going to ask the user to somehow provide a function that does all of the work that we need to do for us, right? All right, so that's a perfect place to stop because we now need to talk about pointers to functions before we can do any of this. All right, so that'll be, I guess, the discussion for next Monday.